Dear students, welcome to another lecture in Elements of Machine Design. So we started this chapter shafts in the previous lecture. Now let us see about the torsional rigidity. You see, torsional rigidity, we from the torsion equation, we can get the angle of twist theta as TL upon Gj, where T is the torsional moment in Newton millimeters and J is the polar moment of inertia. Sometimes some people write J as IP also. It is units are mm to the power 4, and G is the modulus of rigidity. This is given in Newton per mm square. Sometimes people denote it by C also, but for us let us use the letter capital G. And theta is the angle of twist, and here one more thing is there, L is the length in millimeters of the shaft. Okay, so for a given specimen, the shaft properties like length is fixed for a shaft. If you take one shaft, its length is fixed. Polar moment, polar modulus J also is fixed. Okay, and material properties like rigidity rigidity modulus, that is modulus of rigidity G, this is also fixed. These are all constants now. L is constant, J is constant, and G is constant. L, J, G are constant. Okay, hence the angle of twist is directly proportional to the twisting moment. So if all the other things are constants, so then theta is directly proportional to T. Okay, so the torque producing twist in a shaft is we can say it is similar to the bending moment produced in the deflection of a beam. Beams, because of the load, bending is produced. Similarly, in shafts, twist is produced. So similar to the uh, flexural rigidity in beams, EI. See this EI. This is called as the flexural rigidity in case of beams which are subjected to bending. EI. E is the Young's modulus. I is the moment of inertia. Similarly, torsional rigidity, this term we use, this is like, E is replaced by G and I is replaced by J. Okay. GJ. See, this thing is called as torsional rigidity. Okay, this how do we define it? It is defined as the torque required to produce a twist of unit radians per unit length of the shaft. See, that means for producing 1 radian, see this theta you can give in degrees or radians. So for producing 1 radian of the twist, what is the torque required? That we can call it as torsional rigidity. So you remember this GJ, this thing that is there down, this is called as torsional rigidity. This is torsional rigidity. Sometimes people may ask, what is torsional rigidity? Rigidity, on the basis of rigidity also we design the shafts. Okay, now see this equation here. Theta uh, is given by uh, the theta is given by T upon G IP. IP means this is J. Okay, that theta is different. Okay, actually there the what theta you used, here they are using as phi. See, the angle of twist phi can be expressed as TL upon GJ. This is the thing that we have used. But this GJ is torsional rigidity. See, I told you J can be sometimes represented as IP also. So this is GJ. GJ is the torsional rigidity. And there is another term, you forget about this one, which is normally used. this term, which is torsional stiffness. Like torsional rigidity is GJ, like that torsional stiffness K. You know, this is denoted by letter K. This is this torsional rigidity per unit length of the shaft. This is what is called as torsional stiffness. So these are the two terms. Just remember, torsional rigidity is GJ and torsional stiffness is GJ upon L. See, one more thing I want to tell you, yesterday we were talking about this formula, P is equal to 2 pi n upon 60. So, here, this T is the torque or the twisting moment. Sometimes, no, it so happens, this torque, no, you have mean torque and maximum torque. See, like a T mean or T max, max, like that. So which is the T that is used in this formula? You see, in this formula, what T torque is used is the mean torque. So you remember this. Sometimes, questions some people may ask: is it the maximum torque that we use here or mean torque? You remember that this is a mean torque that we use here, and this is our torsion equation. No, in this torsion equation, here torque is used. This torque, T. See, this, no, here the torque that is used is maximum torque. Because from this only, will be designing. So, designing is always for maximum conditions. So, if we take average values and design, when maximum values come, it may break. Okay. So therefore, you remember in torsion equation what the T is used, that is maximum torque, and in that power equation what is used is the mean torque. Okay, let us see another example problem. A solid shaft is transmitting 1 megawatt. Mega is 10 to the power 6 watt at 240 rpm. This is capital N. Determine the diameter of the shaft if the maximum torque transmitted exceeds the mean torque by 20%. See, there is mean torque also, and also there is a maximum torque. Take the maximum allowable shear stress 60 MPa. That is, this is the top, permissible top. Okay. So the power is 1 megawatt. That is 1 into 10. Oh, it is not 106. Please. I see sometimes the computer typing, it gives problems. This is 10 to the power 6 watts. Okay. And then Newton, the speed is N is 240 rpm. T maximum is 1.2 times. 20% more means what? 100% is, if you say 100% is 100, 20% is 0.2. So that's why 0.2 more. That is 1.2 times of mean. Okay, and tau is given as 60 MPa. See, MPa and Newton per millimeter square, this is same. 1 MPa is 1 Newton per millimeter square. Therefore, 60 MPa, we can write it as 60 Newton per millimeter square. So, now we have the power equation. In this power equation, what torque is used? It is a mean torque is used. Here, no finding of the dimensions, though mean torque. Okay. So, this is 1 into 10 to the power 6 into 60. So, if you substitute all these values, you will get Newton meters. Why Newton meter? Because in watt, no, meter is there. So, what is, when this equation, when power is put in watts, what you get is Newton meter. So, that you have to convert it into Newton millimeter. Okay, that is into the power 10 to the power 3. Okay, what is watt? Watt is watt is what is the unit of watt? It's joules per second, I think. Joules per second. Joule is Newton meter. Newton meter per second watt. Okay. So that's why there is a meter there in watt. So therefore, what comes is Newton meter, and then Newton millimeter for converting it. You see, you should put all values in millimeters, then only your answers will come correctly. Otherwise, no, in the units itself, though you will be solving the problems correctly, because of the confusion in the units, your answer will be wrong. Okay, so convert it into converted into Newton millimeter. So torque required, maximum torque transmitted is maximum torque is 1.2 times of T mean. So what you got is T mean. You multiply it with 1.2 and then you will get maximum torque. So for this maximum torque, then you have to you have to take in the problem. So you have maximum torque T is equal to pi by 16 tau d cube. This is the formula. T is equal to this. So in that, no, pi by 16 and no, tau is 60 is given here. See, tau is 60. From there, d cube alone is unknown. So from this, you can find out what is the diameter. Okay. Okay. Let us see another example. Now find the diameter of the solid steel shaft transmitting 20 kilowatts at 200 rpm. The ultimate shear stress. See, this is ultimate shear stress. This is not permissible shear stress. Permissible shear stress can be directly taken. Ultimate shear stress, if it is given, then this should be divided by factor of safety. This factor of safety also is given, 8. So 360 by 8 will be your permissible shear stress. If the hollow shaft is to be used, first he talked about solid shaft. Now he is saying hollow shaft. If a hollow shaft is used in place of the solid shaft, find the inside and outside diameters when the ratio of the inside to outside diameter is 0.5. That is di upon do is 0.5. That is what is given. So what are given? Power is 20 kilowatts. Kilo means 10 to the power 3. So 20 into 10 to the power 3 watts. N is 200 rpm. So the ultimate shear stress is 360 MPa. And factor of safety is 8. So first you can find out tau is equal to ultimate shear stress upon factor of safety. See, 360 upon 8, that is coming to 45 Newton per mm square. See how much is this? 360 is the actual strength and we are saying only 45 is the strength. That means so much of uncertainty is there, because of which high factor of safety is taken. Normally factor of safety 2, 3, 4 are normal. 8 is very high. Maybe for some applications it may be necessary, because sometimes if it fails, it may cause lot of damage to the property and also to life. So to prevent that, they may take high factor of safety. Okay. So anyway, we are assuming now we have to take, instead of 360 Newton per mm square, our strength is only 45 Newton per millimeter square. That's what we have to say take. Okay. And what is given? K is given. K is in different places K is used for different things. See here, K is the ratio of di upon do. This is 0.5. Okay. Now once you see now the power equation you have, P is equal to 2 pi n T upon 60. So from that, T is equal to P into 60 upon 2 pi n, and P 20 into 10 cube into 60, 2 pi into n is 200. So from this I told you, because you are using watt, what you get is Newton meter. So you have to convert it into Newton millimeter. You convert it into means just multiply it by 1000. Okay. So this you get torque. So here it is a mean torque. But anyway, they are not talking about mean torque, maximum torque. So the same torque can be used here. Only when the problem comes, no, you should use this maximum torque here, and maximum torque is so much times more than the mean torque. Then only you have to use the you have to increase it to maximum torque. Okay, we know that the torque transmitted is T is equal to pi by 16 tau d cube. So from this, you see, you will get d cube. From that you will find out what is d. D is coming to 47.6. So 47.6, you have, when you round it, you can round it to 50. Why 40, not 48, 49, but only 50? This is some standard value. Even if you see, you will not have data books at that time to choose standard value in the exam. So if you said 48 also, no problem, nobody is going to mark it as absent, as wrong. Okay, now design of the hollow shaft. See, the inside diameter, outside diameter are di and do. So where in case of hollow shaft, see, only the formula changes. T is equal to pi by 16 tau do cube into 1 minus k to the power 4. Yesterday we have seen how from where this formula came. Okay. So see, all the values, just put the values and you will get the answer. So do is coming to 48.6, that is 50, and the I is coming to half of that, that is 50 point, multiply by 0.5 and you will get 25. You see the same thing. You see, if you see here, here also D is 50 and with solid shaft. Here now we are seeing this hollow shaft also is 50, but in the inside no so much material is removed, only 25 m, diameter 25 hole is there. That means how much weight is reduced. Even then it is able to transmit the same power. So that's why hollow shafts are can transmit more torque compared to the solid shafts. Okay, sometimes shafts are subjected to bending moment only, but it is a very rare case. You see, when you say shaft, it should be able to transmit torque. But okay, for a theoretical purposes, let us assume that shafts are transmitting only bending moment. When the shaft is subjected to bending moment only, then the maximum stress is given by the bending equation. Here, no bending equation we are going to use. See, bending equation. We are see when it is subjected to pure torsion, then maximum shear stress theory of failure you be studied. No, in that the uh, maximum principles maximum shear stress theory there we use. Here maximum principal stress theory we have to use. Okay, you remember Rankine theory and those other theories, guess theory and other things. You just refer. Whereas if it is only torque, we use maximum shear stress theory. When it is bending moment, we use maximum principal stress theory. In torque, maximum shear stress theory. In bending moment, maximum principal stress theory. Okay, this is the bending equation. M upon see, actually there will be three terms in bending equation. So two terms we are taking and seeing. M upon I is sigma b by y. So M is bending moment in Newton millimeter. I will be I is the moment of inertia mm to the power 4, and sigma b is the bending stress Newton per mm square, and y is the distance of the neutral axis to the outermost fiber. This will be in millimeters. So from this I is what? For a circular shaft, I is pi by 64 d to the power 4. Okay, and y is half of the diameter, that is d by 2. So if you substitute all these values, you will get this equation. M is equal to pi by 16 sigma b d cube. This is the second most important equation in shafts. First equation is T is equal to pi by 16 tau d cube, and second equation is M is equal to pi by 32 sigma b d cube. See, here instead of T it has become M. Here instead of 16 it has become 32. Here instead of tau it has become sigma b. All the other things are same. So this is the second most important equation. You remember this. And if it is a hollow shaft, what happens? If it is a hollow shaft, no, I becomes pi by 64. Instead of simply d to the power 4, it becomes do to the power 4 minus di to the power 4. So that means, no, this can be written like this. Pi by 64 do to the power 4 into 1 minus k to the power 4, where k is di upon do. Okay, so when you substitute again in the torsion equation, this becomes M is equal to pi by 32 sigma b do cube. See, this much term is same for solid and hollow, but only this term comes extra for the hollow shaft, 1 into k to the power 4. Okay, from this equation you can find out the diameter of the hollow shaft du, and then using the relation k you can find out di also. Okay, now let us see another problem. This is only subjected to bending moment, no torque. A pair of wheels of railway wagon, the axle you have seen, are carries a load of 50 kilonewtons at each axle box, acting at a distance of 100 mm outside the wheelbase. You see, this is one wheel of the trains, there another wheel, and between them 1.4 meters is there. See, this is the broad gauge. Broad gauge is 1.4 meters. Meter gauge will have only 1 meter. Narrow gauge will have 670 millimeters. Okay, that must you remember. You see, what is the difference between narrow gauge, meter gauge, broad gauge? Okay, ours, in Jalgaon, what is there is called a broad gauge. Throughout India, we are having broad gauge only, but there are some places where they are using meter gauge. Now, meter gauge, in some places you have Okay, anyway, uh, okay, meter gauge you have in some places. Yeah, okay, uh, okay, I think this thing there, the train, no, from Charlesgaon to which place? Jamner or something that goes, must be meter gauge. And, there one which come down to Akola to what is that place? Achalpur or something. That is meter gauge. Okay, some trains are there which run. Okay, and the narrow gauges you can find out in hill stations and all like Ooty and maybe Darjeeling and some such places in the hill stations you may find. Okay, anyway, now W is this one acting here at a distance of 100 mm from the wheel. Okay, outside. You see, how do we know there is this side, that side? This problem also is given along with the question. That's how you will know. It should be given. Okay, so on this side 50 kilonewtons, that side 50 kilonewtons. Okay, on the axle it will be coming. Okay, that is the weight. And L is 100 mm. This is L 100 mm, and X is 1.4 meters. This is 1.4 meters, means in millimeters it will be 1400 millimeters. And sigma B is given 100 MPa, that means 100 Newton per mm square. So the axle with wheels is shown in figure. A little consideration will show that the maximum bending moment acts on the wheels at C and D. See here it is like it is simply supported beam at C and D. On this side now 100 mm away, and that side 100 mm away we are having two loads. Okay, and if you remember how to do, how do you find out the bending moment, say from the I don't know engineering mechanics or strength of materials, from those subjects, if you find out, you will find out that the maximum bending moment takes place here at C and at D. See, the entire shaft is A to B. Okay, and the wheels are at C and D, and the bending moment maximum will be coming like this. This is like a cantilever. You see, this much if you see, no, this is support and this is a cantilever. So bending moment, bending moment diagram. If you draw, it will be triangular diagram like this. It comes like this down. Okay, so here will be the maximum bending moment. So what is the maximum bending moment coming at C? That will be, say, 50 kilonewtons, 50 into 10 cube, and the distance is 100 mm, so that will be 50 into 10 cube into 100, that is 5 into 10 to the power 6 Newton millimeters. This will be the maximum bending moment coming at C. This is also symmetric, so D also it will be the same. So the maximum bending moment may be obtained as follows. Okay, see, how do you get it? How do you getting, say, bending moment at A, at this point it is 0. Similarly at B is 0. At C is, see, this is not MA, this is capital M suffix A. This A should be down. In computer typing it comes like this: MC down, that is M suffix C is 50 into 10 cube into 100, that is 5 into 10 to the power 6 Newton millimeters. Okay, and D also it will be the same, and again B it is 0. A and B 0, C and D, this is the value. Okay, and um, now we know that the entire shaft, the both entire shaft, if you see from here to here, maximum bending moment coming is here. Okay, and here. So that is where the material can, the shaft can fail. So that is where we have to design it. So what you will do, you have to use that formula. What is that formula? M is equal to pi by 32 sigma b d cube. So M is 5 into 10 cube. That means you are either designing it C or D. Okay, the same thing. Okay, this is okay. In this, no, your sigma B also is given 100, so only D is unknown. D is coming to 9.82. So instead of 9.82 D cube, sorry. So D cube value is this. So from that you will find out it is coming to 79.8. So you can safely take it as 80 mm. This will be the diameter of the shaft. Now we have solved this problem considering only the bending moment. But shafts normally, what you see in practice, they are subjected to combined twisting moment and bending moment. So when a shaft is subjected to combined twisting and bending moment, then the shaft must be designed on the basis of the two moments simultaneously. That means T also, M also. Okay. Various theories have been suggested to account for the elastic failure of the materials which are subjected to various types of combined stresses. See, there are principal stress. Oh, sorry, theories of failure. Theories of failure we have seen. So in that maximum shear stress theory or guest theory, this is used, for ductile materials such as mild steel when torsion is coming, and a maximum normal stress theory or maximum principal stress theory, which is the Rankine theory. This is used for brittle materials such as cast iron. But even if it is not brittle material, but only bending moment is coming, there also we use this theory only. Okay. So, see, tau is the shear stress induced due to the twisting moment. Sigma b is the bending stress induced due to the bending moment. So, according to the shear stress theory, is tau maximum is half of square root of sigma b square plus 4 tau square. And see, substituting these values of tau and sigma b, tau can be written as 12m, 16t upon pi d cube, and sigma b can be written as 32m upon pi d cube. Okay, if you substitute this, you will get something like this. Tau maximum is equal to 16 upon pi d cube square root of m square plus t square. And this m square plus t square, this term, this term is known as, here it is written, the expression, this term is known as equivalent twisting moment, which is denoted by T suffix E. The equivalent twisting moment is defined as the twisting moment which when acting alone produces the same shear stress as the actual twisting moment and the bending moment. Yeah, that he has not said that, but it should be there. By limiting the maximum shear stress, tau maximum equal to the allowable shear stress, then for the material, the equation 1 may be written as tau equivalent is equal to square root of m square plus t square. That is, tau equivalent is pi by 16 tau d cube. Simply, instead of t is equal to this, now we are saying te is equal to this. That's what we are saying. Similarly, see, for this is for tau maximum, and here sigma b maximum. Sigma b maximum also for from principal stresses, we know that this is equal to half of sigma plus square root of half of sigma square plus 4 tau square. So instead of sigma b you take, for sigma b this is the value, here also sigma b, and here tau. You just replace this and you simplify it, and you will get an equation like this. And this now we can write as, say, pi by 16 sigma b maximum d cube is equal to half of m bracket m plus square root of m square plus t square. Okay, so this equation again, this half of m plus square root of m square plus t square, this is called as equivalent bending moment. Like we are having equivalent twisting moment, we are having equivalent bending moment. So this equivalent bending moment is equal to half of m plus square root of m square plus t square, and this is equal to pi by 32 sigma b d cube. So finally what you get is, what you get is this only, the me. See, earlier we were having the formula m is equal to pi by 16 sigma b d cube. Now we are having me is pi by 16 sigma b d cube. See, me is what? It is defined as the moment which when acting produces the same tensile or compressive stress as the bending moment and the twisting moment combined together. Here also he has eaten this word. Okay. Okay, then today we will stop here. You know these formulae. bend torque equivalent formula and moment equivalent formula. Thank you.